In today's lesson, we'll continue our study of random variables by learning about continuous random variables as opposed to discrete random variables. A discrete random variable commonly arises from situations that involve counting something, like the number of heads in 3 tosses of a coin. Situations that involve measuring something often result in a continuous random variable, and examples could be things like the heights of females and the time to run a mile or something like that. A continuous random variable takes on all values in an interval of numbers. The probability distribution of x is described by a density curve, and the probability of any event is the area under the density curve and above values that make up that event. Now, I hope that you'll recall density curves from Chapter 2, so don't forget that a density curve is always on above the horizontal axis, and it always has area exactly 1 underneath it. We really dealt with kind of 2 types of density curves in Chapter 2. One was a uniform distribution, and don't forget that the area has to be 1 under that, and we'll talk about that more in just a minute. We'll have an example. And then also don't forget that normal distributions are also density curves, and the area under a normal distribution is also 1. So let's start with a uniform distribution and how we'll work problems involving uniform distributions. First of all, let's think about choosing a random number between 0 and 1, allowing any number between 0 and 1 as the outcome. So that means 0.5 could be an outcome, 0.276 could be an outcome, 0.8592 could be an outcome. So as you can see, there are infinitely many outcomes there. So if I want the probability that x is equal to exactly 0.2, well, 0.2 is, there's only one number that's 0.2 between 0 and 1, and there are infinitely many numbers between 0 and 1, so I really have 1 divided by infinity. That's 0. The probability assigned to exact numbers in a continuous distribution is always 0. But I can find the probability that I'll get a number in an interval of numbers in that between 0 and 1. So let me explain what I mean. If I'm picking a number between 0 and 1, every number in that interval is equally likely. So I have what we call a uniform distribution. In order to make the area be 1, since the length is equal to 1, then this height must also be equal to 1. Let me put that somewhere else. Let's see. So 1 here. Okay. So if I want the probability that I'll pick a number between 0.2 and 0.6, then what I really have to do is find 0.2 on here. It's about here. Here's 0.6 here. I want the probability that I'll choose a number between 0.2 and 0.6. So really all I have to do is find the area of that particular region. Well, I can see that 0.6 minus 0.2 times 1 will give me that area. So this length times this height. So it's 0.4 times 1, or 0.4. There's a 40% chance that if I pick any random number between 0 and 1, I'll get something between 0.2 and 0.6. So let's extend this just a little bit. Suppose I define a continuous random variable to be the numbers between 3 and 7. So I want to know what the height of a density curve is that would describe that. Well, since I'm going from 3 to 7, I know that that is 4 units long. So don't forget I have to make my area be equal to 1. So I need 1/4 times whatever that height is. I need 4 times whatever that height is to be equal to 1. So if I divide by 4, I get a 1/4. My height needs to be 1/4 to make a legitimate density curve. So now I can answer any probability question about that. So what's the probability that I get a number above 4.5? We'll just pick a kind of place about where 4.5 is. I want the area of this rectangular region. So to get the probability, I just find 7 minus 4.5, so what this length is, times the height, which is a fourth. And if you do that computation, you'll find that that probability comes out to be 0.625. Notice that I had no equal to in my greater than there. Because the probability of being exactly 4.5 is 0, we won't distinguish between greater than and greater than or equal to in continuous random variables. Now that's not the case in discrete random variables, so you'll have to be sure to distinguish between those two things. So when I get ready to do part B here and find the probability less than or equal to 5.2, well, 5.2 is maybe here, and I want this area. So the area is 5.2 minus 3 times the fourth, and that comes out to be 0.55. I think I meant to have another one, and maybe you do on your paper. There's a D question, and for some reason it's not here, but it says find the probability that your x is between 3.2 and 6.4. So again, I just need to see that that area is 6.4 minus 3.2 times a fourth, and that comes out to be 0.8, I believe. Okay, so here we're always finding the area of a rectangle, and we don't distinguish between a strictly greater than and a greater than or equal to or less than or equal to. And then finally, don't forget that normal distributions are also probability distributions, and they're density curves. So we're going to do problems similar to the ones that we did in Chapter 2, and I think you'll feel comfortable doing these, and I think it's a good time to review them. So our example says the weights of 3-year-old females closely follow a normal distribution with mean 30.7. So let's draw this normal curve. Here's my mean at 30.7. And it says the standard deviation is 3.6. So that means my standard deviation is about 3.6. If we randomly choose one 3-year-old female, I want to find the probability that that female weighs at least 30 pounds. So let's mark 30 pounds is maybe somewhere about here. So I want to know the probability that that female weighs more than 30 pounds. Now I think you'll see here that my answer should be more than 50% because 30 is below the mean of 30.7. So I hope that you'll recall here, if I want to find the probability that x is bigger than or equal to 30, that what I need to do is find a z-score for this. And I hope you can remember the z-score. If you can't, I'll help you. It's the observation minus the mean divided by the standard deviation. And don't forget, all this is doing is finding how many standard deviations above or below the mean our particular observation is. This comes out to be negative 0.194. I'm glad it's negative. I expected that because 30 is below the mean. So I'm looking for the probability that I would get a z bigger than or equal to negative 0.194. So what you'll do here is use normal CDF. So normal CDF, and then if you'll recall, you put your lower bound, which in this case is negative 0.194, and your upper bound, which is infinity. Just in case you can't remember how to find this, you press number 6 for statistics, and then number 5 for distributions, and then number 2, normal CDF. And then in that you'll have to put your lower bound you'll find that that probability is 0.577. So this means that there's almost a 58% chance that a randomly selected female, a 3-year-old female, will weigh at least 30 pounds. You have your quiz questions here. One of them is related to the same distribution for 3-year-old female weights, and then the other one is back to a uniform distribution. So please complete your quiz and post your answers on Blackboard.